Welcome to The Explainer. Today we're going to break down one of the most powerful tools out there for making sense of the world, and that's regression.
So, how can we actually predict the future using data? I mean, it sounds a bit like magic, right? But really, at its core, it's all about finding patterns that are hiding right there in plain sight.
You know, a lot of the time, data just starts out looking like a big cloud of points, kind of messy. But if you look closer, a pattern starts to emerge. Take this car data, for example. As a car's weight goes up, what happens to its fuel efficiency, its MPG? Well, it pretty clearly tends to go down. Now, it's not a perfect one-to-one relationship, but you can definitely see a trend in that cloud.
And that right there is the core idea of regression. It's about taking that messy data and turning it into a clear, predictable relationship. So today, we're going to build this whole concept from the ground up, step by step. You ready? Okay, let's dive in.
All right, first things first. Before we can build anything, we need to understand the two basic roles our data can play in any kind of analysis.
The easiest way to think about this is cause and effect. You've got an input feature, that's the cause, the thing you're controlling or observing, and then you have the output feature, that's the effect, the thing that changes in response. So, going back to our car example, the weight is our input, and the fuel efficiency, the MPG, that's the output we're watching.
And these patterns, they basically go in two main directions. You've got your positive relationships, whereas one thing goes up, the other thing goes up too. Think higher horsepower, bigger engine. Makes sense, right? And then you have negative relationships, just like our car example. Heavier cars, lower MPG. As one goes up, the other goes down.
Okay, so we can see the pattern in that cloud of data points with our eyes. But how do we capture it? How do we make it useful and, mathematical? Well, it's actually pretty simple. We draw a line right through it.
Let's look at a really cool real-world example. A study found that the farther north a fiddler crab lives, so the higher its latitude, the bigger its shell tends to be. I mean, look at that data. It's a bit scattered, which is exactly what real-world data looks like, but that upward trend is totally clear. This right here, this is the heart of what we call simple linear regression.
And here's the amazing part. Every single straight line, it doesn't matter how complicated the data seems, is defined by just two things. First, you have the intercept. That's just the starting point, where the line hits the vertical axis. And second, you have the slope. That's just how steep the line is.
So for our fiddler crabs, the slope is 0.488. Okay, what does that actually mean? Well, it's not just a number on a chart, it's a predictive key. It means that for every single degree of latitude you go north, the model predicts that the crab shells are going to be about 0.5 millimeter wider. Think about that. That's the real power here, turning a simple pattern into a tool that can actually make predictions. All right, so we need to draw a line. Easy enough. But wait a second. You could draw a ton of different lines through that cloud of data points, right? I mean, literally an infinite number of them. So how in the world do we know which one is the best one? How do we find the best fit line?
Well, the secret isn't about what the line hits. It's actually all about what the line misses. To find the best line, we have to measure the errors. Basically, the distance between our prediction and what really happened.
So in the biz, we call these little errors residuals. And you can see them right here. They're just the vertical distances from each actual data point to the line we drew. Each one is a little prediction error. Of course, in a perfect world, all our points would be right on the line and we'd have zero residuals. But, the real world is messy.
So the best line is simply the one that makes all these little errors, these residuals, as small as possible. The computer's job is to find the one single line that minimizes the sum of all those errors. That's why it's called the least squares regression line. It's the line with the least amount of error, giving us the most accurate model we can possibly get.
Okay, straight lines are great. But let's be real, the world isn't always a straight line, is it? So what happens when the pattern in our data is curved?
This is the perfect example. Let's go back to our car data. If you try to force a straight line onto that, it's a pretty bad fit, right? It just completely misses the real relationship. But look at this. If we use a curved line, it captures the pattern almost perfectly. And this is exactly what we call polynomial regression.
And this really opens up a whole new world of possibilities. Now we can use curves to model more complex stuff. But we can even take it another step further. What if it's not just one thing affecting the outcome? With multiple regression, we can use more than one input feature at a time. So, for predicting MPG, maybe we use a car's weight and its acceleration. The more relevant info we add, the better our prediction gets.
All right, so far, everything we've predicted has been a number, right? Like MPG or shell size. But what if the thing you want to predict isn't a number at all? What if it's a choice, like yes or no?
I'm talking about questions like, is this customer going to leave our bank? Or something much more serious like, based on its size, is this tumor malignant or benign? These are yes or no questions.
For this kind of problem, a straight line won't work. We need a different tool. It's called logistic regression. And its whole job isn't to predict a number, but to predict the probability of something happening, a probability between 0 and 100%.
Now, instead of a straight line, logistic regression uses this really cool S-shaped curve. And there's a great reason for that. Think about it. A straight line could easily go below 0% or above 100% probability, which makes no sense. This S-curve is brilliant because it's always squished between 0 and 1. It perfectly maps an input, like the tumor's radius, to a clean probability.
So, how do we get our yes or no answer? Well, first the model spits out a probability. Then we just apply a cutoff. Usually it's 50%. So if the model says there's a greater than 50% chance the tumor is malignant, we classify it as malignant. If it's less than 50%, we classify it as benign. Simple as that. It turns a probability into a decision.
So you see, from finding simple patterns with straight lines to predicting these really complex yes or no choices, regression is this fundamental way that we make data useful. It's all about finding the signal in the noise.
Regression is an absolutely powerful tool for finding patterns, but here's the catch. What happens when we mistake a pattern for a cause? This tool is incredible at showing us what is related, but it can never tell us why. And that's a much, much deeper question. Something to keep in mind the next time you see a chart that connects two things.